Okay, so also the same procedure can be applied to boundary conditions, right? So in boundary conditions, the scenario is a little bit different. Even if you have a structured mesh, you may only be able to use one side of the domain, right? So again, there are two different ways to deal with boundary conditions. One type of ways is to use the ghost point approach. So let me summarize. The first is a ghost point. Is to basically you have a domain and you have your discretization, but I'm going to be constructing ghost points even beyond the domain for me to use. Okay, but the ghost point is not just involved in one discretization. It has to be. I mean, the scenario where ghost point is useful is when both the boundary condition and the interior can make use of the ghost point. So I'm just going to give another example. Let's see what examples. Okay, so let me just give another example. This is actually called neither Dirichlet nor Neumann boundary condition. It's called a mixed boundary condition. Some people call it a Robin boundary condition. Okay, so the Robin boundary condition is basically the derivative and a solution. There is also a coefficient. Added together is equal to something. Okay, so this is basically a linear combination of the solution and the value is null. So this is compared to Dirichlet is basically U is equal to U0, and Neumann, that is the derivative of U is equal to some null. So if you think of a heat conduction, these actually three different boundary conditions corresponds to very real physical scenarios. The Dirichlet boundary condition, if the solution is temperature, means that, well, you fix the temperature at the boundary, right? The boundary is in contact with some very conductive material, something whose conductivity is much higher than the domain, and with the temperature being measured, right? So that's Dirichlet boundary condition. How about Neumann boundary condition? If you have a heat conduction problem, what does it mean by fixing the temperature gradient? Heat flux, yes, right. So basically, you know, from the simple law of heat conduction, you know the temperature gradient is proportional to the amount of heat, the rate of heat going in that direction, right? So if you know the gradient in the direction normal to the boundary, you know the rate of heat that goes into the boundary, right? So this is the case when you know the heat flux. I mean, if you shine the infrared light on whatever piece of material, Neumann boundary condition is probably the right thing to do. And how about Robin boundary condition? That means the temperature. Yes, you have a question? Natural what? Right. I mean, the Robin boundary condition is actually, yes, the basically saying that the linear combination of heat flux and the temperature is equal to a certain thing, right? So for example, I can easily construct a case where I have an environmental temperature and I also have the temperature on the boundary. Then the heat flux is being proportional to the difference between the environmental and the boundary temperature. That's naturally a Robin boundary condition, right? So the ghost point approach is basically saying that I'm going to discretize this. My U1 minus U minus 1 over 2 delta x plus AU0 is equal to B. I'm going to combine this with the heat equation, which is U1 plus U minus 1 minus 2U0 delta x squared plus F equal to 0. So these two combined is going to cancel this ghost point. All right, and that is going to give me the discretization. And the second scenario is instead of using a discretization and the ghost point, I'm directly going to be manipulating the manipulating the differential form in doing Taylor series analysis. So in doing Taylor series analysis, I can easily say that now instead of discretizing the scheme as what we do before, which uses actually the external point, the ghost point, I can just restrict my scheme to not using any outside point. Instead, I'm going to use the boundary condition. So here, what I can do is instead of combine it with unknowns, let's say A times W1 plus B times W minus 1 plus C times W0. I'm not going to do this. Instead, I'm going to be doing A times W1 plus C times W0 plus B times this guy. Okay? B times the derivative of W plus W at x equal to 0. All right, so basically, instead of using the ghost point, what I don't know, I'm going to be replacing it with the boundary condition, something I do know. And I'm going to be doing the same thing as what I did in the last page, manipulating all the Taylor series, plugging terms over here, and then canceling all the terms, right? I'm going to be deriving different A's and B's and C's that actually incorporates the boundary condition into the equation. So this is basically two different approaches regularly used to deal with boundary conditions in finite difference. All right, any questions? Okay, so I will see you on Wednesday to start finite volume, and I'm going to be holding office hour in my office. Again, building 37, 4th floor. Room number is 412.